Hello students, today in our new session, this session is about the lesson work, energy and power, and this is going to be the first session. Today we are going to see the chapter which deals mainly with the mechanical energy and its two types, which are namely kinetic and potential energy. This chapter aims at developing a good understanding of these three physical quantities, namely work, energy and power, and their physical significance. Particularly today we are going to see the important topics of work, work done by a constant force, work done by variable force, and last we are going to see about the energy. Work. The term work in physics is treated as a physical quantity with a detailed definition. When we think of work, we think of jobs, tasks, labor, and generally we think of something that is hard to do. Usually the students also think that it's very hard to learn a new lesson like that. Example, students having a new lesson or holding a heavy weight above the ground. And however, the scientific definition for work is done when a force moves its point of application along the direction of its line of action. So here F is referred as the force which is applied to do the work, and dr resembles the displacement in some direction. We will accept the work only if there is a displacement in the work. An expression for the work done W by the force on the body is F vector dot dr vector. Work is said to be done by the force when the body, that means when the force is applied on a body, it displaces it. See, here you can see the person is displacing a object or a body to a few distances. This is called the displacement dr, and the total work done is equal to F into dr. Here you can see some angle, but we will see about this angle in another picture. The product of F dot dr is a scalar product. In SI system, the unit of work done is Nm or Joule J. Its dimensional formula is ml square T minus 2, which is W is equal to F dot dr cos theta. You may have a doubt that why or how the angle came here. Actually, this theta is the angle between applied force and the displacement of the body, right? This is the applied force and this is the displacement of the body. I will show it in another picture. See, in this picture you can see this is the applied force and the displacement of a body. So it have an angle. The work done by the force depends on the force F, displacement dr, and angle between them. Next one, work done is 0 in the following cases. First one, when the force is 0, that means F is equal to 0, what will happen? Let's see. For example, a body moving on a horizontal smooth frictionless surface will continue to do so as on no force. That means not even the friction is happened here. and it is acting along the plane. This is an ideal situation. Second, when the displacement is 0, that means the dr is equal to 0. For example, when the force is applied on a rigid wall, it does not produce any displacement, hence the work done is 0. You can see here the F is equal to 0, that means the body moving in a horizontal smooth frictionless surface will continue to do so as no force, even the friction is not acting on the plane. This is the picture for the F is equal to 0, and here dr is equal to 0. This man is pushing the this box with a tough energy, but it's not moving, so the displacement is equal to 0. Like this, is carrying a book more than its limit. The third one, when the force and displacement are perpendicular, that means theta is equal to 90 degree, okay, like theta to 90 degree to each other. When a body moves on a horizontal direction, the gravitational force mg does no work on the body. Since it acts at right angles to the displacement as shown in the figure, in circular motion, the centripetal force does not do work on the object moving on a circle, as it always perpendicular to the displacement. See, for a given force F, the displacement dr and the angle theta between them decides the value of work done. There are many examples for negative work done by a force. In a football game, the goalkeeper catches the ball coming towards him by applying a force such that the force is applied in a direction opposite to that of the motion of the ball till it comes to rest in his hands. During the time of applying the force, he does a negative work on the ball to stop the ball which forces towards him. Work done by a constant force. What is meant by this constant force? See, when a constant force F acts on a body, the small work done dW on by the force in producing a small displacement dr is given by the relation dW is equal to F cos theta dot dr. So the total work done in producing a displacement from initial position Ri to final position Rf is W is equal to, that means we are derivating this equation, W is equal to integral Ri to Rf dW. If you integrate that, then you will get W is equal to Ri to Rf integral F cos theta into dr. You can have this F cos theta out of this integral value. So Ri integral Rf dr is equal to F cos theta into Rf minus Ri. That means final position minus initial position. See, the area under the graph shows the work done by the constant force. Here this is F cos theta and this is the Ri and Rf. So the work done towards this F angle for a distance you can be calculate that by subtracting Rf minus Ri. Next one, work done by a variable force. When the component of a variable force F acts on a body, the small work done dW by the force in producing a small displacement dr is given by the relation dw is equal to f cos theta dr, and f cos theta is the component of the variable force that we already saw in the earlier slide. Here f and theta are variables. The total work done for a displacement from the initial position Ri to final position Rf is given by the relation W is equal to integral Ri to Rf, which is dW is equal to integral Ri to Rf f cos theta into dr. The area under the graph is the work done by the variable force. See, according to the variable force, okay, the vertical axis, it has some ups and downs in the vertical axis. That means which is in the component of variable because of the variable forces. The displacement is slightly changed. Now you can have this as another graph for your reference. Next one is energy. Energy is defined as the capacity to do work. In other words, work done is the display of energy. That is why work and energy have the same dimensions, which is ml square t minus 2. See, if a body is able to do work, it is said to have an energy. It requires energy to move a body over a distance. If we had no movement would occur. Okay, if you have no energy, then no movement would occur. When an interchange of energy occurs between two bodies, we can consider the work done as measuring the quantity of energy transferred between them. So totally energy is defined as the ability to do work. We all need some sort of energy to do work. So work is related with the energy. For an isolated system, sum of all forms of energy, that means the total energy, remains the same in any process, irrespective of whatever internal changes may take place. This means that energy disappearing in one form reappears in another form, and this is known as the law of conservation of energy. Energy can neither be created nor be destroyed, but it can be transferred from one form of energy to another. The mechanical energy is classified into two types. One is kinetic energy and another one is potential energy. The energy possessed by a body due to its motion is called kinetic energy. The energy possessed by the body by virtue of its position is called potential energy. The SI unit of energy is like work done, that means Nm Newton meter or Joule J. The dimension of energy is like work done ml square t minus 2. Now using this SI unit and this dimensional formula, you can see how the energy and work are interrelated between them. The other unit of energy and the SI equivalent values are, left side we have the units, that means 1 ERG in CGS unit, equivalent in joule 10 to the power minus 7 joule. 1 electron volt, 1 EV is equal to 1.6 into 10 to the power minus 19 joule. 1 calorie, 1 cal is equal to 4.186 joule. 1 kilowatt hour, how we measure the usage of current is by kilowatt hour, that is 3.6 into 10 to the power 6 joule. Students, remember, these are very important one word questions you may get in your examinations. Thank you, students. This is the beginning of a new lesson. So we have to travel a lot for this work, power and energy. So stay with me. Let's listen and learn.